if you look at these examples, what you want to do is identify the example that is a quadratic function. So what's the number one rule to be a quadratic function? It has to have what? A squared term. So in the first line, you're supposed to circle all the ones that have squared terms. And in the second example, you're supposed to cross out all the ones that don't have squared terms. So if you look there, you would have 2 circled in the middle on the top, and on the bottom you have 2 X's on the second and the fourth. So the ones that we crossed out or didn't circle, what type of graphs will they give me? We focused on them for a long time. What type of graph will this, and this all end up being?
Fuzzy.
The ones we circled are going to be used. Yeah, like a line. They're just normal. They're just lines, guys. These are linear equations. They're y equals mx plus b. So, today is a lot of information. Today is describing how to interpret the equations. Now, what's super nice is the equation that we're going to interpret mostly today is going to be vertex form. And vertex form is very, 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 very similar to the form of an absolute value equation. So an absolute value was y equals a, absolute value, x minus h, absolute value, plus k. The only difference now is where those absolute values are going to be parentheses and squares. So when you looked at the absolute value function, h and k give you the vertex, or the tip of the v. In vertex form for a quadratic, h and k are also going to be the change where the u is a min or a max. So we don't call it a tip of a v because a parabola isn't very pointy, but it does have that valley or the peak. So the h comma k is going to be our valley or our peak for quadratics. Take a minute for the next one, read through it, and sort of summarize them in your own words. So when you look at these two, they're just giving you why we would use one equation versus the other. So we like vertex form for graphing. So vertex form is graphing friendly. Standard form is solving friendly. So when you're looking at these, and like right there, it says find the solutions. We use standard form for solving. We use vertex form for graphing. So again, it's showing how the graph is transformed. Vertex is graphing, standard is solving. So when we get equations of functions, those are typically how you want to look at them.
When's our next day off?
Monday the 16th or next. It's an okay day.
Yeah. How do you do that?
So, now, when you look at these two equations, and again, I just put the two equations here. Do not rewrite them, please, because there's not a space for it. I know, I warn you. The vertex from vertex form is h comma k. The vertex in standard form requires some goofy algebra. You got to take the number on the middle term, divide it by 2 times the first number, and add a negative. And then to get the k value, you got to plug it in. So when I say graphing from vertex form is much easier, It is because the vertex or the valley and the peak are given to you right in the equation. Where in standard form, you gotta kind of find them, which takes some time. The axis of symmetry is going to cut your graph in half. It is always an x equals equation. So it is an equation. You must have x equals. If you do not have x equals, then you have not given the axis of symmetry as an equation. You've simply given me a number. The y-intercept is actually the one that's easiest seen in standard form. And again, if you're in physics, that y-intercept is the starting height. So oftentimes if you get a problem in physics and it's like the person is standing on top of a building that is 64 feet tall, the end number on that equation is 95% of the time going to be that 64. Unless there's some other goofy multiplication or numbers on the other side, the starting height, if somebody is throwing stuff off a building, is going to be this last number here. The max or the min, similarly, is the peak of the quadratic function. So again, if you're in physics and you're talking about throwing a ball up in the air, you now know that the k value in this form is going to be that max height. And I know he probably doesn't give you them in that form, but I will show you in the next couple of days how to transform it so that you can see that number much more easily. This chart is going to be your best friend. Because if you can memorize and understand this, then you can do everything we need to do in Chapter 5. So we talked a little bit when we did the homework about understanding how the graph is changed. And yesterday, all the graphs we looked at had 0, 0 as their vertex. Well, today we're going to move those vertexes. Those vertexes are no longer going to be nice 0, 0s. So if we move the graph horizontally, so the blue one is the parent function and the red one is moved. That red graph is moved to the right. So horizontal translations are movements right or left. They affect the h part of the vertex. So if it's only moved horizontally, the vertex will be h, 0. And the equation would be y equals x minus h squared. There would be no k or a, because the only movement is left or right. If your graph is moved up or down, then our k value is going to be affected. And our function will look like y equals x squared plus k. There will actually be no parentheses on this function. Now, we know that life cannot be that easy and the movements aren't only just right, left, or up, down. Oftentimes, our movements are in both the horizontal and vertical direction, thus giving us the vertex of h, k, and making our equation the infamous x minus h squared plus k. So what I like to do is put words to these images. How do I describe these graphs? Well, let's look at a couple examples and answer all of those questions. When you graph a quadratic function from vertex form, the best thing to do is to identify those three key parts. What does A, H, and K look like? So in this case, remember the general form is A, x minus h squared plus k. That makes my A positive 3. A positive whole number tells me that this graph is now being stretched by 3 units per number. So it's getting taller and narrower. The equation itself is x minus. So just like absolute values, the opposite of what's inside is what you put down. So since it's x minus 4, we put a positive 4.
So it's always going to be a positive.
No, it's always going to be the opposite of what it is in the equation.
Okay.
So if it had been x plus 4,
Yeah.
this would be a negative.
Okay.
Yep. So h equals 4 tells me that this graph is shifted right 4. And k being a negative 2, because k is what's outside those parentheses, tells me that this graph is moved down 2. So the A, the H, and the K have the exact same transformation movements as they did on an absolute value graph. So if that was an absolute value and H was 4, it would go right 4. If it was K negative 2, it would have gone down 2. So my vertex is H comma K. Well, I just found H and I just found K. So my vertex is 4, negative 2. The axis of symmetry is always x equals, and it's always x equals h. Well, h is 4. If A is positive, I have a min. If A is negative, I have a max. So A is positive, therefore I have a min, and the smallest value that this graph will ever reach is negative 2. So I have a min at y equals negative 2. What was the domain of an absolute value? Guess what the domain of a quadratic is? Yep. Their properties are so similar. Oh my God. Similar. The range is similar as well. If the smallest number on the parabola is at negative 2 for y, means all the y values have to be bigger than negative 2. So my range is y is greater than or equal to negative 2. I know it's not on there, but if you were to sketch this, think about what this just said. It said it moved right 4. So I'd go 1, 2, 3, 4 to the right, and down 2. So my vertex would be over here instead of at 0, 0. That's the difference from yesterday. Now, I told you that every graph of a quadratic is a transformation from this table here. So what you would do to get your points for this graph is you actually have to do 2 things now. When you plug in the number, you could plug in 3. So what it's going to do is it's going to be 3 minus 4, which is negative 1, but a negative is always positive when you square it, so you get 1. That gets multiplied by 3, and then move down 2. So you could take the parent function, 1, multiply it by 3, because that's the next step to the right, and then minus 2. So it would be like 3 minus 2, 4, 1. So you would put in your 4, 5, and 6. So again, you're just going based off where your vertex is. And then you just multiply this number by the A and then subtract K. So, is that one? You would multiply by your A. So 4 times 3 would be 12. Subtract 2, and you get 10. So when x was 6, y would be 10. So you just take your perfect square values, you multiply by A, and add or subtract K to get your y's. Okay, let's look at example 2. A is the number out in front, so A is -2. H is the opposite of what's inside, so -1. And K is what's being added or subtracted, so a +4. My vertex is H, K. My axis of symmetry is x equals the -1. This time, A is negative, therefore I have a max at 4. Domain never changes. If you have a max, that's my highest point. So now all the y's are less than that value. So if you have a min, they're greater than. A max, they're less than. If you made a table, what would you put in the middle? Your vertex. Then you'd go above and you'd go below. You got, yes?
How do you tell if it's max or min?
The A value. So if A is positive, you have a min. If A is negative, you have a max. Again, you have 2 choices right now. You can plug 0, 1, -2, -3 into the function. So you want to plug them in on the calculator and do the math mentally. Or you can take the 1, the 4, and the 9. Well, actually, in this case, it'll just be the 1 and the 4. You can multiply them by -2 and add 4. So 1 times -2 is -2. -2 plus 4 is 2. Take the 4, multiply by -2, be a -8. -8 plus 4 is -4. So again, if you have that 0, 1, 4, 9 memorized, you just multiply by A and add K, and that will work every single time. The only ones you have to know is how to find the x's, which you just take your vertex, H, and go to the right and the left in the same way you did with your absolute value. The x's are the same. So you have 0, 2, -1, +4, you have -2, 2, and -3, -4, and 2, -4. So you can see that this is stretched. It's much more narrow. It's reflected. It's moved left and up 4. I know this is a lot of information. It feels a lot of new information, but once you get that pattern down, it's not as bad as it appears. The last problem would be, okay, I'm only telling you 2 points that are on this graph. You have to figure out the equation. So the equation is ax minus h squared plus k. I give you that the vertex is at 3, 7. So that means that h equals 3 and k equals 7. I also give you one other point. I give you the point 9, 4. So what that means is that x equals 9 and y equals 4. Well, if you look here, doesn't my equation have y, h, x, and k's all up there? What letter am I missing that I usually know? Well, I'm missing a. So what I'm going to do is plug in h, k, x, and y and solve for a. So I'd have 4 equals a, 9 minus 3 squared plus 7. Now you just do your order of operations the same way you would do it. 9 minus 3 is in the parentheses, so you do parentheses first. 6, so you have 4 equals 6 squared times a plus 7. What is 6 squared? 36. Isolate your a by subtracting 7. Divide by 36. So you found your a. Next, all you want to do is plug back in a, h, and k. That's probably the hardest problem that we're going to entail for this unit. We're going to do many, many, many more practice problems to make sure we can do those ones. What I want to do tonight is just look at a couple of graphs and a couple of finding your axis of symmetries.